Okay, so let me erase this part. So this one here is the architecture I'm going to speak about next. I think in the next hour, I think for the newcomers very quickly, this is the inner loop. This is just stabilizing. This is the outer loop to track a certain signal. It could be the pitch rate, it could be the altitude, whatever. It's a tracking problem. Okay? And we have an integral to remove the steady state error in the system. And I will show you where this is coming from in a minute. All right? So the new topic is basically tracking controller via integral control. Tracking controller via integral control. So this is the architecture that we have. Let me change some of the nomenclature here. The output here is Y, right? The output here is Y. Let's call this EI. EI, is that what I call it? Yes, EI. Let's call this one here XN. And that's R, and the rest is the same. Right. Okay, so this is our architecture. I mean, in your notes, you can write this topic and maybe put it down here. And my claim is that the error here will go to 0 as time goes by, and this is the goal here. The goal is to bring this EI to 0, because if that's 0, then we have achieved our tracking problem, like the altitude, the pitch rate, and all that stuff that I just explained to you in the previous hour. The goal is to bring this guy to 0, because what we are trying to do is we're going to write this time R versus Y, right? And then if you have an input of RC, do it like this, RC, we want this Y to follow that with 0 steady state error, right? This is the goal. All right, so the way I'm going to do this now, I'm going to write down the equations, and we'll move from there. This part we have already done. We know this part. This is what we have done in the previous weeks, and this part is now new. So let's just write down this new part. This xn, you can write it like this. Let's do it this way. Okay, that's the first equation. Xn dot is equal to EI, because I'm taking, this is the integral, right? I could have written 1 over S, right, as an integral, but I don't, because I'm not writing this in the Laplace domain. This is not in the Laplace domain. I'm just writing, this is a block diagram, but I have signals, and this is a state space representation. So it's not really a Laplace, a block diagram in Laplace domain. So that's why I have this integral sign here. Okay. So xn is the integral of EI. Therefore, xn dot would be equal to EI. right? So if I take the integral of xn, it will be xn. And this is equal to EI, and EI is RC minus C times x, which is equal to y. Okay? All right, good. And a second one, I have x dot is equal to ax plus bu. That is my linear system. And y is equal to c times x. So now you have an extra state over here. So you could actually write this in Laplace in a state space form. Xn dot is equal to A0 minus C0 x xn plus B0 u plus 0, 1 RC. Y is equal to C0 x xn. Okay, so I just wrote this in a matrix form, and note that A is a matrix by itself, so therefore this is not really a single number 0, so everything else is 0. Okay, so this is a matrix. This is here a vector or a matrix, and this is 0. B is a matrix, and so on and so forth. So whenever I wrote a 0, it means, actually, maybe I should be doing this. It is the appropriate matrix, 0 matrix. It's the appropriate 0 matrix. It is not only a 0, it's a 0 matrix that corresponds to the appropriate size when you write A and C and B in these equations. Okay? So far so good. But there's one more thing here. This U is equal to minus k times x plus, ki times xn. So this is no more r here. So just remove this r. Your notes for this. Let's make this ki to say this is the integral controller. Ki over here. So it's ki times xn. So this is ki times xn over here. Ki times xn. That's that signal minus k times x. That's equal to u. And that's here. So you write this, you put this into this thing here. You will have x dot is equal to ax plus b times minus kx plus ki times xn. Which will give you a minus bk, okay, times x plus bki times xn. Right? And xn is this one. So rewrite that equation over there, rewrite the matrix, the state space representation. Space. Rotation. And you obtain this. X dot is equal to xn dot A minus bk times ki minus c 0 x 1 R, y is equal to C 0 X XN. And this is now your final representation of your state space model. So I'll talk about this in a second. Okay, now if you look at this, we have now a state space system which is a little different than before. The A matrix of this closed loop, so this is now the final result, right? The input here, this is RC, sorry. Okay, so this is like the command. Anywhere I'm missing this again? Here RC, okay, RC, so this is RC. So now you have a new system. I mean, this looks like that. This part here is the new A matrix, right, of the state space representation, of the system matrix. This is the B matrix, and this is your new C matrix. So in fact, and this is now your new state, right? This is your new state matrix. So you basically have a new system, again with A, B, and C. It's a linear state space. It's an LTI system, but the states are no more X as it was previously in our closed loop. Now the states have another member. Okay? And one of the members here is Xn, which is here. And it is not really a state that belongs to the linear system anymore. It belongs to my controller. Now the controller itself has another state, which I call Xn. And in fact, it is part of the state space representation. It is Xn dot, and therefore there's an Xn, right? And Xn is here as well. So we basically have a new state. And this is what we would call a controller state that appears in my state space representation. Yes?
How can we show that X dot and Xn dot have same dimensions?
They don't. X dot, X and Xn don't have the same dimensions. They don't have to. Okay? Let's say X has X1, X2, and Xn is equal to X3. Not same dimensions. So what's going to happen? You will have 1, 2, 3, 1, 2, 3. Because you have the A matrix, this will be a 2 by 2, and this will be whatever it is, because whatever, oh, and here you will have 0 anyway. So then this will be a 3 by 3. As an example, right? 2 states, 1 state, X dot Xn will be, I'm sorry, X and Xn will be X1, X2, X3, 3 states. Okay? So X and Xn don't have to be the same state at all. In fact, what we are looking here, if it's a typical tracking problem, the way I explained it in the last hour, you would typically have one input here and one output here. So you would be tracking the altitude or the state or the pitch rate or the roll rate, whatever. So this would be a single state. Okay? So typically this is a single state, and therefore this is a single state. But this could be multiple states. Make sense? Okay. So they can be different states. So xn is a new state. In fact, it's a state of a controller. It comes that the state really appears because of the controller. It has nothing to do with that. But now the total system looks like that, where xn is part of my design now. It's part of my states. And it increased the number of states and therefore the number of unknowns in my A matrix. Now here's a question. If I want to stabilize this system now, this system over there, what am I going to design? I'm going to design this. I'm going to design this. Previously, I had, if this was a second order system, I had two k values, or depending on the number of states, I had to design k's. Now I have an extra member here. I need to design ki. I need to design k and ki in such a way that this A prime matrix is stable or has the eigenvalues wherever I want them to be. So if I would give you a problem saying that let's move the eigenvalues here, 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 then those eigenvalues have to actually match the state space system, because this system now represents that. Okay? So here is the problem that you would see. The problem will say, let's say I have an airplane that is linearized at blah, 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 and here's your matrix. Okay? And then I would tell you two things. First of all, stabilize the system, move the eigenvalues over here. Secondly, design an outer loop to track altitude. Okay? Then you would need to write this and calculate k and ki such that the eigenvalues of this system, of the whole system, is the eigenvalues of A prime. That's a good question. The question is this. You might say, well, we learned how to calculate k. We did that in the exam, right? Or in the homeworks. So let's calculate k with Bhaskara and all that stuff the way we calculated before. And then write it down over here. And then only calculate ki. That doesn't work. Unfortunately, it does not. K and ki now are coupled, because they are now in this thing, so you cannot calculate them independently. The observer gain, remember in the last 2 weeks ago, the observer gain can be calculated independently. This cannot. Okay? So therefore, you have to calculate k and ki independently. So in other words, if you have an architecture like this, the Bhaskara and all that stuff goes away. You have to calculate this and this independently. In fact, those k's will be different. Okay? Any other question? Yes?
I couldn't get that. How can we add RC comment directly by matrix? Because there is an integral over there.
Well, I just wrote the equation that this is what comes out. What you mean here?
Yes.
Just do them. I just wrote these things down. Wrote down the equations, and this is what comes along.
There is no RC over there. There is an integral.
Where do you mean?
The RC over there.
Do you mean this?
Yes.
Yes, but I have EI, and EI is equal to xn dots. So xn dot is equal to xn dot is equal to that. Xn dot is equal to r minus y times r. It's because of this. So r is here. You see? Xn r, you see, minus c times x. It's actually this equation. This x looks like a subscript. It's not. It's c times x. Okay? Any other questions? I mean, from now on it's simple. I'm just going to make a just going to do an example, so it should be straightforward from here. But there's one thing I would like to show you, and it's this tracking problem business. Is that me? Sorry. So sorry. Any questions so far? No. So my claim was that this will remove the steady state error at the end. Right? If you give a command like this, if this is RC, and you want to look at Y, the Y would be somehow oscillate or something and then sit on this thing, right? That was the claim. So maybe I should first do an example and then work on this. Not sure if which one I should do first. Well, anyway, let's do that. So, claim is that this architecture, this control architecture, will remove the steady state error. State error in the tracking problem. Okay? Because I told you we could be removing that integral and just have that, so it will be just a tracking problem, right, without the integral. That's what I showed you in the last hour. You could remove this, and it would still be a tracking problem. The only issue is that you would have a steady state error, and I will show you now why. Okay? This will just remove the steady state error. This controller architecture will remove the steady state error. So let's take a simple tracking problem and look at the steady state error. This is not a good controller without a feedback gain. Okay. Okay, let's do it like that. So, write this system in using Laplace. Oh, let's do it this way. Let's do it this way. Isn't that how we did this? Let me give it a second. Okay. This is here y. Okay? Just to make it simple, make this one equal to v, so that it's k times r. I mean, it's the same problem. Let's call this b, just to make it simple. Okay? So, And let's call this one A prime. Because I'm going to write stuff there, so it will not be very crowded. Okay, let's call this matrix A prime, and let's call this one V. It's K times R. It's just a multiplication of K times R. So this is what we had in the last hour. So what we're going to look at, we're going to look at the response between Y and V. Okay, V is the input now, and Y is the output. Okay, and this is your system, and this is what we had in the previous hour. So we're going to use Laplace to show you one thing. Okay, to show you one thing. And you realize that this is now a single input, single output system, right? Let's make it simple and say this is single input, single output. Because the single input is R, and the single output is Y. Input, single output. Okay? Although it is X, and X is not necessarily a single input, single output system. And this can, in fact, be a closed loop system. Closed loop. Closed loop. We call it inner loop. So basically what I did was I took this part, this red part, and said this is one system, and I'm not going to, write more stuff in it. So this is just that. Okay, so this is without integral. Okay, there's no integral here. Not an integral controller. But it is a tracking problem. You see that, right? Tracking problem. This is a single input, single output tracking problem. So this is a very special case here. Okay. So, because it's a single input, single output, I can write a transfer function and use Laplace. Let's do that for this one here. S times X is equal to A prime X plus B times V. Okay, so I just wrote this one here. And Y is equal to C times X. So you take that, this will be Si minus A prime times X is equal to B times V. So Y will be equal to C times Si minus A prime minus 1 times BV. So Y divided by V will be equal to C times Si minus A prime minus 1 times B. And this one we will call a transfer function. At the same time, E is Y of S. V of S. We just write this down and then we'll talk about this. So first write it down and let me explain it. For those who weren't here in the first hour, please watch this from the videos, okay? Because in the first hour, I tried to explain what's a tracking controller, what is a stabilizing controller, how do you marry them in order to make the actual controllers, where do you use them, and all that stuff. If you just came for the second hour, it might be just a little confusing at this point. So, let's look at this. We just wrote this. We said this is our new state space representation. And now I'm going to look at the relation. We are looking at the transfer function between the input, V, and the output, Y. Okay, we are looking at that transfer function. It's over here. So that's what we are looking at. And this one we obtained, I think, before. We'll do that real quick. X dot AX plus B times B times K times R minus C times X. Oh, that's not what we really did. Sorry. Just 1 second. So anyway, I mean, I think there's another C here because of that thing. Okay, this is Y times BC. There might be another C, but the dimensions might be screwed up. I would rather just do this. Let's just put a V over here and call this the input without really confusing us too much. Okay, so please make it a V, because if it's K times X, then it should be coming from here. But because we have that output feedback now, it should look like this. And V represents basically the output over here, whatever that is. Okay? So this is our state space representation, and we are looking at the Laplace transform, and it's right here, Si minus A prime, X, blah, blah, BV. So you obtain Y. You're looking at the input-output relationship here. Y is equal to C times X, and this part here is X. Right? And you can see it. You take it to the other side. It will be Si minus A prime over minus 1 times BV. So that's X. So this is Y. So you look at the response between Y and V. V is the input, Y is the output, and it will look like that. Okay? And because you have an S over here, if you write this correctly, this will be the transfer function between the input and the output. Okay? What you want is that Y and V, they should cancel each other, right? That is the plan. The input and the output should be the same because that's a tracking problem. So that is gone. That's your error. So Y of S is the transfer function times V. That comes from here. Transfer functions times V is equal to Y. And then if you write it into the aerodynamics will be like this. Vs is equal to 1 minus T of S. And at the end, in terms of Ts, if you write what we have found here, you will find the aerodynamics that look like this. Okay? And you want the aerodynamics to go to 0 as time goes to infinity. Okay? This is what we are trying to do. And in order to do this, if you have a transfer function like this, right? This is the transfer function. This is in the Laplace domain. This is the S over here that we have. So we want to look at this. What happens as time goes to infinity? In order to look at that, we can use the finite value theorem. Okay, and that will look like this. Limit at S goes to 0, S times E of S. Okay, I hope you remember this from system dynamics. You use the finite value theorem to see what happens as S goes to as T goes to infinity. What happens to ES? And this is simply you multiply S with ES and as S go to infinity. So it will be S times this thing, V of S, 1 minus C Si minus A prime times B. Now V is the input. What we're going to look at, if I give an input, what's going to happen? So let's give an input of 1. So let's give a step input. Okay, so V as in time, it will be like that. Okay, so it's a step input. The way, if that's true, if this is your step input, then V of S will become 1 over S, right? Something you probably have done often in system dynamics. And limit S goes to 0 is S times 1 over S times 1 minus C S I minus A prime B. They will cancel, of course. With S equals 0, 1 plus C. Oh, there's a minus 1 over here, right? 1 minus there's a minus 1 here. Okay, here there's a minus 1 because of this. And here's a minus 1. Sorry. Here's a minus 1. C times A prime over minus 1 times B. And this is as ES as time goes to infinity. So this is the value of ES as time goes to infinity. And ES is the difference between VS and YS. And you want that to be 0 as time goes to infinity. And you can tell that it will not go to 0 all the time, depending on B, A, and A prime. So let me write it down here. E of S does not always go to 0 as t goes to infinity. In fact, it will depend on C, A prime, and B. Right? It will depend on C, A prime, and B. It will depend on this, C, A prime, and B. For a given step input, will I have my steady state error at 0 or not? It will depend on C, A prime, and B. You could have a combination of C, A prime, and B such that this goes to 0 at all times. For this, I'm not sure, because I don't know what these values really are, and I know B, C, and A prime can be a lot of things, and therefore this might not go to 0. But let's check this one here. This is the integral controller. Just remove this one. And this is my steady state system now. This is my steady state. This is my A. It's here. C is this one. And B is here. This is my new steady state system. Now the question is, would that go? Would the steady state here go to 0? So let's look at that. E of S as time goes to infinity. Or let's do it like this. E of S, this is probably not very nice to say. Let's say E steady state, okay? Because E of S was basically the transfer function. Let's say E of S, the steady state value. E of SS, simply that 1 plus C, A minus 1, B. Okay? Write it down. Let's do it for this one. It's equal to 1 plus C is C 0. A is at A prime over minus 1. And B is B. Or let's just keep it that way. And this is a steady state error for this. Now we need to do an example and see what will actually come out of this. Okay? To make sure that this actually works. Okay, so we have a 45. Let's give a short break, really, a 5-minute break, okay? Then I'll do an example.